Okay guys, we're going to continue to look at polynomial functions, these functions that have maybe one or many terms where all of the exponents are non-negative integers and all of our coefficients are real. But as we have these polynomial functions, the interesting thing is no matter what their degree is, all of these functions have something in common, and that's their graphs are all very smooth curves that are continuous. That is to say that they don't have any breaks in your graph where you'd ever have to pick up your pencil. And we don't have any sharp turns. So we could see this first degree linear function here, a very smooth curve, no breaks. Our second degree looks like a quadratic function shifted down 3 here, an opening down, but you know, it's smooth also. Our third degree function here, I kind of wrote a third degree, this looks like a nice smooth curve. Fourth degree, nice smooth graph, and fifth degree, we could see that all of these have in common that they have smooth and continuous curves. So keeping this in mind, that polynomials behave this way, nice smooth curves, then what I want to be able to do is just look at these over here and classify which ones would be a polynomial and which ones would not. And so I want you to take a moment to look at these here and consider the fact that we can't have any sharp bends and we also can't have any discontinuities. Do any of these graphs exhibit those two behaviors? Or do any of these graphs look like they are smooth and are looking like they're polynomials here? So looking at what we do have over here, starting with number 11, we see a curve here that is definitely smooth throughout. And I didn't have to lift my pencil up to draw it. And so that being the case, we would definitely say that something like number 11 is a polynomial function. Now number 12, definitely I wouldn't have to pick my pencil up at all to draw this absolute value curve that's been shifted to the left. But the key here is that we have a sharp bend in our curve here. And so because we have this sharp bend, it's not that it's not a function, it's just that it's not a polynomial function, okay? And so of course we could write the equation of this absolute value graph. It would have been some absolute value graph shifted to the left, some, I guess, C units. It wouldn't matter here, but you could see that this doesn't look like a polynomial function's equation. So number 13 here, taking a look at it. Definitely a lot smoother than we saw in number 12 here. But the fact is we have to satisfy both the fact that it's smooth and continuous. And the fact is right here, this graph actually has a vertical asymptote, it seems, that exists between the two branches of it, of the hyperbola is what we would call this graph. But basically, this would mean that you'd have to lift your pencil up from left to right to start your graph up again. So because there is we're going to write a discontinuity, it is discontinuous there, then we would say that this is not a polynomial. So in your best judgment, looking at number 14 here, would we have a polynomial graph? Well, you know, smooth, and we don't lift our pencil up, so pretty easy to spot a polynomial graph. We have these smooth curves that are everywhere continuous. Cheers.